Good afternoon, everyone. Welcome to another RISP webinar, RISP Masterclass webinar. And good morning to those who are in the West or in Adelaide, South Australia. Welcome to another RISP Masterclass webinar. My name is Sudha. I'm part of the senior leadership team at RISP, and I oversee the products and data systems, and I will be your host for this webinar. Before I proceed any further, I'd like to acknowledge the traditional custodians of the land where we meet today. And for me, in Perth today, that's the Whadjuk Noongar people. I would like to pay my respects to their elders past and present, and extend the respect to Aboriginal and Torres Straits Islanders people with us today. It is an interesting topic that we're going to discuss today, and it is my absolute privilege to introduce Aaron Fraser, the Engineering Director, Systems and Software at Wabtec Corporation. Let me quickly read his bio. Aaron Fraser is a highly accomplished railway signalling and systems engineer with 2 decades of experience delivering cutting-edge signalling solutions across Australia, New Zealand, Italy, and North America. Renowned for his strong leadership and technical expertise, he possesses an advanced understanding of railroad technologies and systems with a proven track record of executing projects through the entire engineering lifecycle. As a qualified project manager and chartered engineer, Aaron excels in leading teams and driving the successful delivery of complex railway projects. In his role as engineering director, he is currently spearheading the technical delivery of signalling controls and communication systems for the Gold Coast Light Rail Stage 3 project. His ability to integrate innovative solutions with strategic leadership continue to shape the future of rail transportation. Aaron, welcome to our Masterclass webinar, and I'm confident that there's a lot of people who are here to sort of hear this interesting topic that you are discussing today. And so before I proceed, let me remind everyone that your questions, please put your questions in the chat. And at the end of the presentation, we will pick out those questions and we'll do our best to answer them. Please be respectful, as this is an open chat for everyone. So please be respectful with your comments and what you put out today. Aaron, without any further delay, over to you for the presentation.
Awesome. Thank you, Sudha, and good afternoon, everybody. All right, so today we're talking about coexistence and interoperability of digital signalling systems. So firstly, Sudha and RISP, thanks very much for inviting me to present. It is my pleasure to try to give back some to the industry and to try to help everyone to grow and learn. So we will be covering quite a bit of information today, so I will be talking relatively quickly. So apologies for anyone that doesn't understand my Australianisms, but you know, such is life. So firstly, we'll be going through an introduction to basically a few definitions around what do I mean when I talk about coexistence, interoperability, as well as the concept of interchangeability. Secondly, we'll be looking at some of the global approaches to digital signalling system implementation and how interoperability has been achieved in those instances. Thirdly, looking at some of the emerging coexistence and interoperability challenges that are occurring on a global level, and then finally adapting that to what's happening here in Australia. So let's start with interoperability. So at its core, this means a system or product can work with other systems or products without needing special adaptations. In accordance with AS 7450, Rail Systems Interoperability, full interoperability of the Australian rail industry would be achieved when any railway system, process or asset can be successfully operated seamlessly across or within multiple operational environments without change to that system, process or asset. Generally, interoperability is made possible through the implementation of standards. When we talk about coexistence, this is a little different. It's when multiple signalling systems operate side by side on the same infrastructure or within the same operational space. A good example is a line where both a national legacy system and ETCS are in use in Europe, with trains running safely under either system. Or where a freight train equipped with a digital signalling system of one needs to run over another network with a different digital signaling system. It's sometimes referred to as partial interoperability and is acknowledged under standards like AF7450. And finally, interchangeability refers to the ability to swap out components or modules like an onboard unit or an interlocking from different suppliers without having to re-engineer or recertify the system. This level of compatibility is rare but highly desirable for avoiding vendor lock-in and simplifying ongoing maintenance and support. So where does interoperability matter and where doesn't it matter? On the left is an image of the Trans-European Transport Network, which is the European Union's strategic plan to build unified multimodal transport infrastructure across Europe. A major pillar of this initiative is the deployment of ETCS on core railway corridors to ensure seamless cross-border interoperability. On the right is an image of the mining railroads in the Pilbara and Karratha regions of Western Australia, where rail networks are privately owned and operated by the big miners such as Rio Tinto, Roy Hill, and FMG. These networks are closed systems with each company running its own dedicated trains, infrastructure, and control systems without the need to share tracks or interconnect with other networks. Interoperability, in this case, is simply not required. Similarly, interoperability between a metro or a subway system and mainline passenger railways typically isn't a priority because these networks serve different purposes and operate independently. Since there's usually no need for trains to switch between the two networks, there is no need for interoperability. Looking at the three global mainstream technologies for digital signaling systems, we have CBTC, or communications-based train control, which is commonly used in metro and urban networks. We have the European Train Control System, or ETCS, which is widely deployed on European and international mainline railroads to achieve interoperability. And finally, we have Positive Train Control, or PTC, which is the standard for North American freight and passenger safety systems and also aims to achieve interoperability. So while these systems were developed for different operational contexts, all three provide core digital signaling functions. This includes sending movement authorities wirelessly, if we only focus on ETCS level 2 out of all the different levels of ETCS, using radio or cellular networks rather than relying on traditional trackside signals. They also provide overspeed protection, helping enforce speed limits and temporary speed restrictions automatically, and they safeguard against an overrun of authority, which means ensuring a train does not go beyond its permitted limit of authority, critical for preventing collisions. So while each system is tailored to its specific environment and the needs of the operator, the core purpose remains the same: increasing safety and efficiency through real-time communication and automation. So the next few sections, excuse me, I'll be stepping through a little bit more detail on each of these various systems, and also providing some level of information around how interoperability has been achieved in each of those different systems. So in Europe, almost every single country used to have, and still does have, its own automatic train protection system. In fact, there's around 20 different disparate systems in place in Europe at the moment. Normally, these systems were not compatible with each other, so crossing a signaling area border or a country border meant the trains needed to implement several onboard ATP devices, each which was standalone and non-interoperable. In some instances, a train had to be equipped with 7 different types of train control systems on board to undertake its journey through parts of Europe. Due to the increase in international rail services, a harmonized ATP system is needed for the European context, and thus the European Rail Traffic Management System was born. Its intent was to gradually replace the different national ATP systems in European countries and to enable interoperability of the national railway systems and allow cross-border operation. ERTMS comprises of the automatic train protection component, which is called the European Train Control System, ETCS, and the Global System for Mobile Communications for Railways, GSMR, or the future FRMCS. Today, ERTMS is mandatory for new EU-funded rail infrastructure, which include new or upgraded signalling, and is increasingly adopted in non-European countries for modern digital rail operations. ETCS consists of a number of different levels, so level 0, NTC, level 1, and level 2. For convenience sake, I'll only be focusing on level 2 for this presentation, as it is the most similar to the other types of digital signalling systems that will be discussed today. So ETCS Level 2 is an advanced train control and signalling system that enables continuous radio-based communication between the train and a centralized control center known as the radio block center. So the radio block center effectively just sends movement authorities to that train to allow it to know, what its limits of authorities are. The system uses trackside balises to provide accurate train positioning data. Once the train passes a balise, its exact location is updated and communicated to the RBC via the GSMR or FRMCS network. The RBC uses this data along with the status of track infrastructure from the interlockings to calculate a safe movement authority and transmits this back to the train in real time. So this approach allows for greater precision in train control, may increase line capacity, but primarily it's used to enhance safety by eliminating human error related to signal interpretation. And also, obviously, it's a key component of the European strategy for interoperable rail systems. So how does ETCS achieve interoperability? Well, there's a set of standards called the Technical Specifications for Interoperability, which are published under what are called the Control, Command and Signaling, CCS, TSI, or Technical Specification for Interoperability. Essentially, the TSI standardizes the air gap between onboard and wayside to enable interoperability and cross-border operation. It enables interoperability by defining standardized functional, technical, and operational requirements that all ETCS Level 2 systems must meet. This includes specifications for the onboard and trackside subsystems, communication protocols, message formats, and interfaces between key components such as the onboard computer and the radio block center. So again, the goal of the ERTMS or ETCS was to standardize that interface between trackside and train-borne equipment. So provided a rail network which owns trackside equipment is able to communicate according to the defined interface, then any train that also respects that interface is able to operate on the network and interoperability is achieved. So now we'll talk a little bit about interchangeability. So while ETCS was designed for interoperability, and it does that again through that defined interface over the air gap, it does not yet fully ensure interchangeability, in the strictest technical sense. In fact, if you look at subset 26, chapter 2, it actually states specifically that no interoperability requirement will be established for external trackside subsystems such as interlockings and control centers. So looking at that diagram, you can see that down here where there's standardized protocols between the onboard and the wayside, when you look at, say, between the interlocking and the control center, that is not currently covered by the ETCS standards. So you can't really just grab a RBC from one supplier and swap it out with an RBC from another supplier because they're all using proprietary interfaces between those products, generally anyway. Transport for New South Wales, as part of their digital signal systems program, has tried to overcome that with a common interface between the traffic management system and the RBCs to enable two suppliers to talk, but that is a bit of a rarity in the ETCS world globally, so kudos to them for the efforts that they've been putting in. So whilst that may be the case in terms of pure ETCS or ERTMS, there are initiatives in place at the moment in Europe to try to establish interchangeability. So ULINKS is a European initiative led by the infrastructure managers with the actual goal of standardizing the interfaces and architecture of railway signaling systems. So from the ULINKS system description document, one of the primary development goals of the ULINKS system is that dedicated functional components or subsystems shall be interchangeable irrespective of the supplier. So the key objectives are to make signaling systems more maintainable, upgradable, and cost-efficient over time. ULINKS supports the wider deployment of ERTMS by eventually enabling components like interlockings, trackside objects, and control centers to be supplied independently and integrated more easily. Ultimately, its goal is to help railways to reduce lifecycle costs, shorten deployment times, and avoid vendor lock-in while supporting a more unified European rail infrastructure through interoperability and interchangeability. Excuse me. Currently, ERTMS implementations do not mandate U-links, although some national railway infrastructure managers have chosen to adopt U-link specifications as part of their signalling modernisation programs, particularly when deploying or upgrading ERTMS systems. So as you can see in this table, so Netherlands, Norway, Switzerland, they're all embarking on key initiatives for upgrades to their signalling infrastructure where they have specified, in some cases, U-links for their architecture to enable that long-term competitiveness and interchangeability between suppliers. So again, U-links is not currently mandated by EU law. It is a voluntary industry-led initiative to standardize signalling interfaces and promote modular, interchangeable, and interoperable systems. So now moving on to communications-based train control, or CBTC. So what is CBTC? It's a modern signalling system used primarily in metro environments to manage train movement with much greater precision and efficiency than traditional systems. It's defined by the IEEE standard 1474, which provides the performance, availability, operation, and train protection performance and functional requirements for a CBTC system. So it is not as highly defined and specified as ETCS, which gives a lot of leeway to the suppliers for how they would like to implement it, and means a lot of proprietary interfaces, as you can imagine. So what sets CBTC apart from other digital signalling systems is its use of continuous two-way digital communication between the train and trackside systems. This allows the control center to know the exact position and speed of each train in real time, instead of relying on block-based detection systems. One of the biggest benefits of CBTC is its ability to use what's called a moving block system. This means trains are spaced based on how quickly they can safely brake, not based on fixed sections of track. As a result, trains can run much closer together, increasing capacity without adding more track, as well as maintaining the safety of the system. CBTC also supports various levels of automation, as shown in the table on the right. In fact, many driverless metro systems around the world, which could be considered anything between GOA2 to GOA4, like in Paris, Singapore, and parts of London, use CBTC to operate safely and efficiently. Just to differentiate CBTC quickly from ETCS, which is used on mainline and generally used on mainline and high-speed routes and is specifically built for interoperability, CBTC is built for dense, high-frequency metro systems. CBTC often uses Wi-Fi or LTE for communication, whereas ETCS, as part of the ERTMS standard, uses GSMR or MCS in the future, and tends to rely on fixed blocks with some virtual enhancements to enable capacity enhancements. So how does CBTC work? Well, it uses communication between the train's onboard computers and wayside zone controllers to precisely track trains and maintain a safe separation based on the performance of the train and its operating speed. Under a moving block system, computers calculate a safe zone around each moving train that no other train is allowed to enter. The system depends on knowledge of the precise location and speed and direction of each train, which is determined by a combination of several sensors, transponders along the track, and train-borne speedometers on board the train. So let's looking at the interoperability and interchangeability of CBTC systems. So CBTC systems are typically not interoperable or interchangeable due to the lack of standardization across vendors. Each supplier, whether it's Siemens, Alstom, Hitachi, or others, generally develops their own proprietary protocols, interfaces, and safety logic. As a result, a CBTC-equipped train from one supplier cannot usually operate on a CBTC line from another without major modifications. This vendor lock-in extends to both onboard and wayside equipment, creating long-term dependency and limiting flexibility in operations and procurement. However, it should be noted that generally CBTC design is designed as a tightly integrated end-to-end system and a closed network. So in most cases, it really isn't an issue. And as we see over in Perth, they've gone with a single supplier for their high-capacity signaling project, and other CBTC networks throughout the world. That's very typical. So it's also very challenging, obviously, because of the proprietary interfaces and the proprietary nature of the CBTC systems to mix and match components from different suppliers. Interchangeability is not something that CBTC was designed for. While there have been efforts such as New York City Transit's I2S standard to promote interoperability, these remain exceptions rather than the norm. And we'll talk a little bit about New York City in the next slide. So whilst commercial off-the-shelf CBTC products generally use proprietary interfaces and are therefore not interoperable, an outlier is the New York City subway's implementation of CBTC, which specifically aimed for interoperability. So just a little bit of background about the New York City subway system for those who haven't had the benefit of utilizing it themselves. It's the 9th busiest rapid transit system in the world and moves around 5.5 million passengers throughout the city on a daily basis. It was opened in 1904 and it is one of the world's oldest public transit systems, which makes upgrading and digitalizing their very old signaling system to a CBTC quite challenging, and as we'll talk about in the next few slides. It also has the most stations, with 472 total across 36 lines and almost 400 kilometres of route length. Another challenge for implementation of signalling modernisation to CBTC is also the fact that it runs 24 hours a day, 7 days a week, 365 days a year. So we don't really get those engineering hours to come in and do incremental signalling upgrades. New York City Transit began exploring CBTC in the 1990s as a way to modernise its ageing fixed block signalling system and dilapidated signalling equipment. The goal was to improve reliability, increase train capacity, and enhance safety. The first major milestone was the Canarsie line, or the L train, which became the pilot corridor for CBTC. Deployment began in the early 2000s, and by 2009, the line was fully operating under CBTC with automatic train operation. Following this success, relative success, obviously almost 10 years to roll out one line was quite a long time. New York City Transit then started a new approach towards achieving interoperability and began interoperability testing with Siemens and Thales on the Culver line. Sorry, I forgot to mention that the Canarsie line was delivered by Siemens. Following the proof of interoperability on the Culver test track, CBTC was then expanded to the Flushing 7 line, which came online in 2017. That line used a different supplier, Thales, which was part of New York City Transit's push for interoperability between systems, to prove that other suppliers were able to deliver and upgrade and modernise the signalling infrastructure. Since then, the CBTC program has accelerated quite greatly and is now in various stages of planning and implementation on other lines, including Queens Boulevard, Culver, and 8th Avenue. And they've also managed to bring on a third supplier, Mitsubishi, as a certified CBTC supplier to continue to improve the competitiveness as well as to prove the interoperability throughout the different systems. So while the rollout has to date been complex due to the age and density of the infrastructure, as well as some of the challenges that they've had in terms of trying to prove and implement interoperability, it has laid the foundation for a more reliable and flexible subway system. Each deployment also builds on lessons learned, including how to manage operations during cutovers and how to maintain service during upgrades. So now let's have a look at how interoperability was achieved for New York City subway. New York City Transit made a deliberate choice to require interoperability in its CBTC deployment strategy. By insisting on interoperability, New York City Transit enabled competitive procurement. This fosters a more open network, keeps costs in check, and allows the agency to choose the best technology for each project phase while also enabling innovation. It also simplifies operations and integration. The New York City, as you saw before, the New York City transit system, the subway system, is a highly complex system. It has many different lines. There's two divisions, the A and the B division, where trains may and where trains may operate on many of the different lines, and in some cases between divisions. So with so many interlining services and with CBTC-equipped trains potentially operating over different lines, upgraded at different times and by different vendors, New York City Transit needed a way to upgrade incrementally without disrupting the broader network. Interoperability provides that pathway. So to achieve true interoperability in its CBTC program, New York City Transit, along with its suppliers, Siemens and Thales, developed the I-squared standard, or the interoperability interface specification. This standard defines how different suppliers' onboard and wayside CBTC components communicate over the air gap in a similar manner to what we saw for ETCS, and as we discussed earlier, something that is necessary to enable interoperability is to standardize that air gap. So basically, it allows trains equipped by one vendor to safely operate over CBTC infrastructure provided by another vendor. The standard was validated through real-world testing on the Culver test track, demonstrating that interoperability between different CBTC vendors is not just theoretical, but achievable. But I will point out that, again, this is a very rare case in terms of CBTC. In most cases, you probably don't need to implement interoperability, and it has been very costly and taken quite a long time for the New York City transit system to implement. But I guess the groundwork has already been there. But whether the suppliers want to support that for standalone CBTC, that's another case entirely that you would need to look at as an operator. So just touching on, New York City Transit has invested, and the MTA has, and the government have invested quite a lot of money in their signalling modernization to CBTC. So it has seen some major benefits from this CBTC investments. So on-time performance has significantly improved on CBTC equipped lines, especially the L and 7 lines, with better reliability and service frequency. Another major milestone, as we've talked about already, is supplier diversity. So we now have Siemens, Thales, and Mitsubishi all certified to implement interoperable CBTC throughout the New York City Transit. So avoiding dependency on a single vendor and creating flexibility for future deployments. New York City Transit is continuing its heavy investment in CBTC with ongoing innovations and an accelerated delivery program with interoperability at its core. Now let's talk about positive train control. The Rail Safety Improvement Act, or RSIA Act of 2008, was passed in response to a tragic incident, the 2008 Chatsworth collision involving a Union Pacific freight train and a Metrolink commuter train. This law mandated the implementation of positive train control, or PTC, on specific segments of the US rail network. PTC was required for all Class 1 railroads on main lines carrying high volumes of traffic or transporting hazardous materials. It was also mandated on any main line used regularly for intercity or commuter passenger rail service. The original compliance deadline was a lofty ambition of achieving full rollout throughout the United States by December 31st, 2015, but it was later extended to the end of 2020. By December 29, 2020, PTC was fully deployed on over 57,000 route miles, with one of the most critical achievements being interoperability. It must be noted that the interoperability was not just a best practice that was aimed to be achieved by the suppliers and by the railroads. It was a regulatory requirement vital to achieving uninterrupted and safe train movement across the national rail network. So what is positive train control? Well, it's a system designed to prevent train-to-train collisions, derailments caused by excessive train speed, train movements through misaligned track switches, and unauthorized train entry into work zones. Wabtec's Interoperable Electronic Train Management System, or IETMS, which I'll be referring to as Wabtec's PTC from now on through this presentation for the most part anyway, was chosen collectively by the Class 1 railroads as the PTC solution for the US national freight network. Wabtec's PTC today is installed on over 90% of total PTC deployment in the United States, and is equipped on over 23,000 locomotives. Today, trains equipped with Wabtec's PTC system complete nearly 1 million miles per day with PTC protection, mitigating potential hazards, costly accidents, and protecting lives. PTC has also been proven to be interoperable with over 70 railroad customers, and many combinations of host tenants had to be considered, including interoperability with some of the other PTC systems, which we'll get to on the next slide. So as I mentioned, there are a number of different PTC systems in use throughout the US. However, Wabtec's PTC, the IETMS solution, which was developed collaboratively by the industry with multiple vendors developing different components of the system, and also collaboratively with the railroads, with some oversight by the FRA and assistance through the Association of American Railroads. So Wabtec's IETMS is a safety critical overlay system providing means to enforce movement authority, speed restrictions, and uses GPS to help reduce the potential for train accidents. While it is one of many PTC system variants in use in the United States, importantly to note, it is the most widely used. And when we consider interoperability, which we get to soon, it is the system that has to deal with the most cross-border operations, as well as transitioning between different operators as a Wabtec PTC or IETMS equipped train has to traverse throughout the United States. So other types of PTC systems in use in the US include Access, which is a overlay to a cab signaling system, mostly in use on the Northeast Corridor by Amtrak, Long Island Railroad, Metro North Railroad, and New Jersey Transit. The Incremental Train Control System, which is a GPS-based system used by Amtrak on its Michigan line. And it should be noted that's also in use on the Fortescue Metals Group corridor here in Australia. We also have EATC, ETMS, and also communications-based train control. So just important to note, as we talked about earlier, where does interoperability matter and where doesn't it matter? Well, most of those systems that I've talked about there down the bottom on the slide, they're in use on passenger networks that are very far away from each other, where those passenger trains that are equipped with those systems will never have to run over another territory that's equipped with a different PTC system. So in that case, interoperability probably doesn't matter. Similarly, with the communications-based train control system that I mentioned there for the Port Authority Trans-Hudson between New York and New Jersey, well, that's a metro subway style system. So it's completely standalone. It's got its own rolling stock. It's got its own CBTC system that's equipped on all of that rolling stock. And quite frankly, there's no other trains that will ever run on that network, and those trains will never run outside of that network. So obviously, there's no interoperability required in that case. Looking at Wabtec's PTC in a little bit more detail. So as I mentioned, it's a safety critical overlay system. So what exactly is PTC? Well, there are four major subsystems in a PTC, in Wabtec's PTC system: onboard, wayside, back office, and communications, which is via the interoperable train control messaging protocols, which is a standards-based system managed by the Association of American Railroads. And we'll talk about that when we talk about interoperability in a little bit more detail soon. So as the train moves along the track, the onboard computer system monitors GPS-based train position and receives track data related inputs from wayside locations and base station radios along the planned route. This provides the train driver with advance warning of movement authority limits, speed limits, and track conditions ahead, giving him time to react and bring the train to a safe speed or controlled stop. If corrective action is not detected within the warning period, the PTC onboard equipment automatically applies the train's brakes and brings the train to a controlled stop. Because PTC is mostly installed on very big, long, heavy freight trains, it must factor in locomotive and rail car mix, train length, weight and speed, terrain and signal aspects to determine safe stopping distance. It has been proven to over many different types of locomotive and passenger rolling stock, and is very much a success story for for implementation of automatic train protection throughout the United States as well as globally. So as I mentioned earlier, when looking at PTC, it is important to consider where interoperability matters and where it doesn't. So pictured here is the North American Freight Rail Network map, showing the vast scale of the American network, including the wide variety of different operators and borders that need to be considered for interoperability. So, if you consider the state borders in a similar manner that you would consider the country borders for cross-border operation in Europe, you can see that the magnitude of the challenge is quite immense. So as mentioned earlier, by law, PTC must be interoperable, meaning that passenger, commuter, and freight trains that are required to seamlessly communicate across all railroad systems. So you can see here the railroad network is quite complex with hundreds of combinations of hosts and tenants, which means, so when I talk about a host, it means who owns the track. And when I talk about a tenant, it's who's operating the train over that track or infrastructure. So interoperability is achieved when the locomotives of any host and tenant railroad or adjacent railroads operating over the same track segment can successfully communicate with and respond to the other railroad's PTC system, allowing uninterrupted movement across property boundaries. As you can see here in this diagram, we have a case where a train owned by Railroad A needs information about a temporary speed restriction on track owned by Railroad B as it approaches and crosses the boundary between the two railroads. So in this case, the onboard equipment of Railroad A is talking to the trackside equipment of Railroad B to obtain that information. And this is all done through standardized messaging protocols that are, again, these are the ITC interoperable train control messaging, which provides all of that standardization between the onboard and the wayside and the onboard and the office systems. To not only enable interoperability, but also, as we'll talk about in a little bit more detail, to enable interchangeability between systems. So there were more than 200 host-tenant relationships that needed to be tested and verified, so quite an immense effort by all of the suppliers and the railroads throughout the United States. The Federal Railroad Administration had to provide guidance and ensure that the requirements were acceptable to comply with the law. All railroads had to submit their PTC implementation and PTC safety plans for Federal Railroad Administration review and approval, identifying all the interfaces and relationships, ensuring all the relevant testing was undertaken, and ensuring all of the safety hazards and safety assessments were undertaken to enable certification of these systems in quite a compressed timeframe. So how was interoperability achieved for PTC? The number one enabler was the law. However, a few Class 1 railroads came together very early on. They had a vision beyond the mandate. They looked at PTC as an enabler, not only to improve the safety, but also help them improve the productivity and efficiency of their operations. They established an interoperability committee called through which they established standards for interoperability. They formed Association of American Railroad working groups, and they also invested heavily in the communications infrastructure, as well as an investment in the positive train control system itself. So through that effort, the United States now has established interoperability standards for the implementation of positive train control to address the federal mandate for improving rail safety and ensuring interoperability through all of those host and tenant railroads. These standards are maintained through the Association of American Railroads and cover all of the relevant interfaces and functions of PTC to ensure interoperability and to allow competition. Interoperability between the trainborne and trackside equipment for any combination of PTC-equipped locomotive and track segment ownership is provided through the use of standard communications and messaging protocols. This standard protocol combination is utilized by each PTC-compatible system, regardless of track segment operator, locomotive ownership, or wayside segment component manufacturers, enabling 100% interoperability throughout the USA's freight and passenger networks. So shown here is a case study which shows just a small segment of what might happen in the day of the life of a train as it operates throughout a corridor on the United States. So in this case, we're showing us a Canadian Pacific train, and with Canadian Pacific crews with a BNSF locomotive in the lead. And it's traveling through various segments owned by different railroads. So in black, we have the Norfolk Southern Railroad. In green, we have the Belt Railroad in the Chicago to Milwaukee part of the stretch of the journey. In blue, we have the Chicago Metro, which is a passenger network. And then in red, we have the Canadian Pacific subdivisions. So how does interoperability allow that train to traverse through the network? Well, the locomotive, the onboard equipment on the locomotive continuously communicates with back office infrastructures for each of the railroads, regardless of proximity to that territory. As that train traverses the network, it talks to all the wayside interface units along the route, regardless of their affiliation with a particular railroad or subdivision. And all of this obviously is enabled through the use of the interoperable train control specifications, as we discussed on the previous slide. So the system allows for any combination of crews, owners, and operating railroads to seamlessly operate over borders and through different operators throughout the United States. Interoperability also had to be achieved where freight trains equipped with PTC, with Wabtec's PTC, travel over a passenger railroad's network equipped with a different PTC system. For example, on the Northeast Corridor, passenger trains use Amtrak's Access PTC system. In this case, interoperability or coexistence is achieved by dual equipping the wayside and the office. The two PTC systems will both utilize temporary speed restriction data and wayside status information, but will receive and process the data independently through their own protocols. Train control sends TSR information to the IETMS boss, as pictured in this diagram, as well as to the Access Safety Server in separate messages, which is sent to the respective PTC onboard units. Similarly, the Access and Wabtec PTC wayside interface units installed at interlocking will function as encoders for each of the equipped trains, respectively. The Wabtec PTC WIUs will communicate with the Wabtec PTC onboards, and the Access WIUs will communicate with the Access onboards. And the respective onboard devices will independently enforce wayside statuses. So you can see that wasn't necessarily an elegant solution that was used for those to achieve interoperability in those cases. However, interoperability nonetheless has been achieved. As depicted on this slide, which is hosted on the Federal Railroad Administration's website. And this was updated regularly through the peak deployment period to highlight the complexity and enormity of the task that was undertaken by the industry, and now serves as a great example of the work that had been undertaken and the great success story that was Positive Train Control as it was deployed throughout the United States. So it should be noted that a project of this grandeur and scale under such an aggressive timeline, 12 years in total, with the first few of those years probably not as rapidly as they probably wanted to, but in the end, 12 years to carry out 57,000 miles of upgrades and signaling modernisation, with 209 host tenant railroads and over 20,000 locomotives installed, as well as training over 100,000 staff throughout the United States in positive train control. Well, it's quite an effort. So congratulations to everyone that was involved, and to the FRA and to everyone that provided oversight to ensure such a monumental task could be undertaken. So finally, let's look at interchangeability for positive train control. And again, when I'm specifically talking about Wabtec's PTC here. So it should be pointed out that the interoperable train control specifications do not restrict the use of, nor do they favour any specific vendor components. As long as if that component meets all functional and safety requirements of the specifications, then it can be used. While it should be noted that Wabtec at the moment is the key vendor of the ITC compatible PTC solution deployed on the Class 1 railroads and numerous commuter and passenger railroads in the United States, the overall solution is not currently dependent on a single supplier. The Wabtec's PTC is trackside communications and back office agnostic. At the moment, from a trackside perspective, WebTex PTC has been proven to interface with 4 different trackside suppliers, including Hitachi and Electrologics, just to name a couple. And how this is achieved through the interoperability spec. So interoperability between the onboard and wayside equipment for any combination of PTC equipped locomotive and track segment is provided through the use of a wayside interface unit whose behavior and communications messaging protocol are standardized. WebTex PTC is also communication system agnostic and supports an open messaging standard. It's back office server agnostic. There are multiple vendors for back office servers that are implemented throughout the United States today that the WebTex onboard is currently talking to. And similarly with the train control systems, there are a multitude of different vendors that are providing train control systems. So there isn't vendor lock in there, and essentially interchangeability for WebTex PTC has been achieved. And while from an onboard perspective at the moment, WebTex is kind of got a vendor lock-in, Siemens and Hitachi are both trying to enter that space with ITC compatible onboard systems. Now let's look at some of the emerging coexistence and interoperability challenges that are occurring on a global scale. So firstly, we'll look at Crossrail in London. So Crossrail was an ambitious project to create a new east-west mainline railway through central London. It's a highly complex arrangement with many interfaces between different new and legacy systems, mainly due to CBTC being chosen as the technology for the central core to enable 30 trains per hour. As you can see in the diagram, there are multiple signaling systems and interfaces between TPWS, AWS, ETCS, and CBTC. So how did they resolve this? Well, they simply triple fitted the trains with ETCS, CBTC, ETCS, and TPWS, with automatic changeover between the systems at the appropriate point. So while each of those systems are well proven in service on their own, it was the changeover that caused the big technical challenge. So one of the saving graces of the program was that only a single type of train is currently used through the CBTC section, the Bombardier Class 345 Aventuras in a 9-car formation. So to triple fit, they basically had to install the signaling equipment for each system on board, requiring installation of specific sensors for each of the different signaling systems, as well as appropriate communication systems, for example, Wi-Fi to support CBTC and GSMR to support ETCS. In this case, they actually used a single DMI that was configured to the different types of signaling and automatically transitions through those as the train hits those transition points. Looking at challenge 2, so an emerging emerging interoperability challenges occurring in Toronto in Canada, where Metrolinx are upgrading their existing signaling system to ETCS level 2. So this introduces some challenges as the tenant freight trains, such as those operated by Canadian National and Canadian Pacific, that use Metrolinx tracks to service their customers will not be equipped with ETCS, and in most instances are already equipped with WebTex PTC. So to overcome this, instead of looking for a native interoperability solution, they chose to look at coexistence and enable this through retention of line-side signals. So the colour light signals were retained and will be maintained for the indefinite future to provide continued support for freight operators, as well as to serve as a backup for ETCS equipped trains for the long term in rare cases of degraded operations. And finally, we'll look at an emerging problem that's occurring on a global scale between positive train control and ETCS. So following the successful deployment of PTC in the USA, freight operators around the world are choosing to look at WebTex PTC as well as other PTC systems to fulfill their digital signaling needs. So in that case, as we see more and more freight operators move towards a PTC solution, given that it's proven to be more suitable and affordable solution for a freight environment, the following challenge is very likely. So where sections of network will be equipped with ETCS for passenger services and where freight trains will be equipped with PTC, there will need to be some sort of interoperability or coexistence solution to maintain operational safety. Since ETCS and PTC cannot currently interoperate with each other, the only real way to do it natively is to either dual equip the trains with both the systems or to retain the wayside signals, both of which are expensive and not desired. So shown on this slide is some of the potential solutions to overcome this problem on a global scale. So I will point out that Wabtec is continuing to investigate these solutions with our partners and clients throughout the world, as we believe this is a critical issue that needs to be resolved to ensure seamless transition between the two systems. So when considering how to achieve interoperability between IETMS and ETCS, there are several technical pathways, as shown on some of which are examples of which are shown on this slide, each with different trade-offs. Some of these options have already been explored in previous studies undertaken by Sydney Trains and ARTC for ATMS and to ETCS interoperability. So I've listed some of those options on this slide, but for the sake of simplicity and without touching on any commercial sensitivities, it really boils down to one, do you want to retain line-side signals similar to what we observed in Canada? Probably the answer to that is no. It's costly. You're going to have to maintain those signals for the lifetime of the asset. Secondly, is dual equipping the onboard, similar to what we saw for Crossrail. Probably not. There's a lack of space on freight locomotives in Australia. It's expensive. You'll have to maintain. You have to train people twice. It becomes a bit of a operational colossus. Thirdly, as we've seen in Amtrak, is potentially to dual equip the wayside or the office. So this means installing two different types of wayside interface units or signaling equipment, one for each PTC system on the same section of track or at the same interlocking. Similar. This approach allows multiple PTC equipped trains from different railroads to operate safely on the same infrastructure, but it increases installation and maintenance complexity, as well as the need for careful coordination between the systems. Other alternatives could be a translation layer or a gateway to enable the PTC system to elaborate its own movement authority, utilizing the underlying safety system, the signaling safety that's in place through the interlockings in the ETCS territory, for instance. And that could be undertaken through a standards-based approach by obtaining the relevant information for the PTC system to elaborate its own movement authority. Another approach could be to translate ETCS movement authorities into PTC movement authorities to assure safety throughout the network, or to have an onboard system that speaks dual languages. Each option reflects a balance between cost, complexity, certification, and operational integrity. And again, Wabtec is exploring how we are going to solve this, because we do see this as an important initiative that needs to be resolved on a global basis. Finally, and I think I'm running out of time, so I'll try to do this relatively quickly, is adapting this to the Australian context. So Australia's rail network is incredibly complex, with 18 different networks, 11 different signalling systems, and many different operational rules and standards. This fragmentation creates challenges for running trains. However, with the rollout of digital train control systems throughout the Australian network, such as ETCS, we now have a window of opportunity to fix this, to prevent a digital break of gauge. So I'd just like to point out some of the great work that's being undertaken at the moment by the National Transport Commission to overcome some of this, with interoperability being a shared goal across all Australian governments. And there will be new obligations under the Rail Safety National Law, including implementation of an interoperability management plan by all the operators as part of their safety management system. Depicted there is the National Network for Interoperability, which you can find more details on the NTC's website. And I'm sure if you do need more details, Stephen Lemon's probably your guy to talk to. So looking at some of the specific interoperability issues that we have here in Australia. So first of all, we'll look over in the west, over in Perth. So the high capacity signalling project is an upgrade to Perth's urban rail network, introducing CBTC to replace the legacy signalling system. It's important to note that the new CBTC system isn't intended to be compatible with freight or locomotive-based locomotive hauled passenger trains, which won't have the necessary onboard equipment. So trains that, whatever the signalling system that ends up being utilised across the national network for interoperability through ARC and ARTC and Horizon, may have to work, won't have to interoperate with CBTC because they have, over in Perth, they have specifically gone for infrastructure segregation where possible to prevent this interface issue from occurring. And in the limited areas where both need to operate, where freight trains with a different signalling system need to interoperate with a CBTC system, traditional line side signals will be retained, similarly to as we saw in Canada, to support legacy train operations. In Melbourne, the Metro Tunnel's initial deployment of CBTC, while offering modern signalling benefits, it does create potential challenges for interoperability with future ETCS rollouts on other adjacent lines and throughout Melbourne. So the current CBTC system in Melbourne is being delivered by a specific supplier with proprietary interfaces, which may limit its ability to interoperate with future ETCS systems, unless specific interface adaptations are developed. I'm not entirely sure how they intend to resolve this challenge in the future, but it may require dual equipping of onboard or development of gateway interfaces, adding complexity and cost. But what is obviously they'll need to come up with some sort of solution to ensure smooth operations between the ETCS and CBTC systems. And finally, looking at Transport for New South Wales Digital Signalling Systems Program, where ETCS Level 2 is being implemented across the Sydney Trains Managed Network. So currently deployment is funded for 2 initial corridors, selected in part because they have no impact on freight operation. However, deployment is planned across the whole network. One of the main drivers of the business case for Sydney was for capacity increase, but also asset rationalisation with associated maintenance gains, particularly through the removal of line-side signals. Because of the significant interaction between the Sydney network and freight trains, interoperability or coexistence between ETCS and whatever ARTC's chosen digital signalling system needs to be considered. Depending on the system chosen, a potential solution, as discussed earlier, for the global PTC ETCS interoperability challenge could be considered. Another aspect that needs to be considered is the rollout of ETCS across the capital cities of Brisbane, Sydney and Melbourne, which also requires seamless integration and interface compatibility along the eastern seaboard. Ensuring that these systems can effectively operate and communicate with each other is vital for achieving interoperability. The NTC is developing strategic policy advice for the nation's transport and infrastructure ministers on a digital pathway for Australia, with priority on this eastern seaboard to ensure interoperability amongst the variants of ETCS that are being deployed. So finally, to sum up, and thank you all for listening, when we talk about interoperability, we're referring to the ability of trains and systems from different suppliers or networks to work seamlessly together. And generally, this has been undertaken through defining the air gap, a standards-based approach between onboard and wayside systems. Coexistence may be achieved through mechanisms like dual fit of equipment, intelligence system in overlays, or messaging protocols. But it's important that signalling system A must be capable of acquiring the information to operate within signalling system B's environment, even if no direct interoperability exists. And finally, interchangeability is the most ambitious goal of the 3, but is only possible when we move away from proprietary protocols and instead use open, standardized interfaces, something initiatives like ULinks are actively working towards. And thank you.
Thanks, Aaron. I think we have almost run out of time. There are a few questions that have come through, and thank you for those who are participating for answering some of the questions that has come through the chat. Aaron, just 1 or 2 questions, and then we'll close off. We're probably going to go a little bit over, but you talked a little bit about interchangeability being an ambitious goal. Is it a concept that you think interoperability first needs to be considered before interchangeability, or should that be considered in the conversation of interoperability itself from the get-go?
I think they're two separate goals. So obviously interoperability is for cross-border operations primarily. So it really comes down to the operator's needs. So if they want to have that long-term flexibility in terms of their supplier arrangement, then interchangeability is probably one of the goals that they should be looking for, which would, enable them to use an RBC from supplier A on one line or supplier B on the same line, rather than being locked into a particular vendor for a particular line, for instance.
And you also mentioned the interchangeability, the standard EU links is voluntary at this particular point in time. And, is there any, why is that, I guess? And is there any plans for are there any pathways to make it a little bit more mandated or stronger in the future?
I wouldn't be able to talk about whether there is a path for the EU to mandate U-links in law. At the moment, it is certainly something that is, it's totally up to the operator whether they want to put that into their specifications when they're procuring an ETCS upgrade or a signaling upgrade, and that's up to them, right? So if they want to work with their suppliers to ensure interchangeability in the long term, as well as some of the overall competitiveness and flexibility, then yeah, sure, they can specify U-links in their own specification. But yeah, as far as enacting it into law goes, I think obviously ERTMS is still relatively fluid. We've just come up with a new baseline. I think was released in November or thereabouts. So there are a lot of configuration issues that are ongoing with the ERTMS rollout on its own. So whether they want to go down that route of including U-links as a default standard as part of that, or in parallel with that, that remains to be determined, and I think would be a lofty future goal.
Couple of one-liner quick questions. A standard interface interoperability specification. I think when you talked about the I2S, when you talked about the New York City systems, the question was, is this available publicly?
I don't believe it's available publicly. You'd need to talk to probably one of the suppliers. I think Siemens might own it, but Siemens under New York City Transit probably has ownership. But I'd imagine you'd need to talk to someone from New York City Transit to obtain that.
And then just one more, is there block diagrams for PTC components available somewhere?
It should be on the Wabtec website, but if you reach out to me through LinkedIn or via email, I'm more than happy to provide additional information.
Well,
and yes, sorry, just to answer Ryan's question, yes, it does provide capacity improvement over other onboard systems, and Wabtec's moving towards what they call PTC 2.0, which is a full moving block system, which will provide capacity benefits for the railway operators.
And that's all we have time for. Thank you very much for a very clear presentation. There are lots of credits for you on the chat as well. So thank you for taking the time to come and talk through this complex conversation and make it very simple for everyone who are discussing. So much appreciated. And thank you for your time for participation. For all of the others who are there, just a quick note that next, for those who are interested, RISB has got standards on interoperability, and also there are 2 standards and other documents. So if you're interested, you can always get onto the website and you can download them, and you can have read a bit of that and the direction that's going. The next webinar is on the 20th of May. The title is Enhancing Railway Safety Through IoT and Blockchain Integration. It'll be a very interesting conversation. So please, if you're interested in that, please jump in and register for that. That's it for us from RISB. Thanks again for everyone for participation. Thanks, everyone.